Okay, good afternoon everybody. We start with session number 7, Medical Industrial Application of Pattern Application. And the first talk is presented by Jesus. We work retinal artery and vein segmentation using the image divisional adversarial technique. 15 minutos.
Thank you so much. I'm really happy to be here. Thank you so much for your assistance. My name is Jesus Gonzalez, and I work on this paper with Dr. Juan Alberto Sosa. We both are at the SIC from the IPN. I'm doing there a postdoctoral. I have a postdoctoral position there. I have been working many years on machine learning, but I realized that a great area of opportunity is apply this knowledge in machine learning on healthcare. So last years I have been really interested on that, and that is the main focus of this paper. That is called retinal artery and vein segmentation using an image-to-image conditional adversarial network. Also, another important thing is that these kind of neural networks are hot topics today, so it's interesting to be applied on healthcare. So this is going to be the agenda, pretty short. First, the introduction, what is important, and what we want to achieve. Second, the methodology. Third, the experiments and results. And finally, the conclusions and related work. So first of all, why it is important. So the improvement of medical service is very related to the advance with the technological things that can be created. So one important thing is that this kind of services sometimes needs very knowledgeable people, specialists on their different areas. So the diagnostic, the treatment, and things like that takes too much time, and this affects directly the quality of the service for the patients. So, and another important thing is the retinal and blood vessels. This is incredible, but this has a lot to do with many diseases. For example, retinopathy, that is a kind of diabetes, So, for example, the caliber of the retinal vessels changes under certain impulses has to do with the kind of the diabetes and with the different treatments that could happen. Also, the visual loss is directly related with the different kinds of diabetes. Also, hypertension, for example, the different caliber on the retinal has to do with the hypertension. Also, Alzheimer. It is incredible for me. It was completely surprised. But Alzheimer's has to do with the vessels, blood vessels on our eyes. So certain kind of biomarkers that has derivative of this retina could help on the diagnosis and treatment of Alzheimer. And of course, tumors like like this one can be detected also with this work. So once we know the importance of this, we have also why we need this kind of segmentation. And this is because on the diagnosis and treatment of this kind of diseases, we first need to want to automate the whole process. And one common first step on this process is the retinal blood vessel segmentation. So this has been tried for a long time from different approaches, for example, image processing, artificial intelligence approaches, different ones, convolutional neural networks, custom deep learning architectures, and image processing combined with deep learning. But then if there exist two different approaches, why it is important to do it again, right? So one thing is that these approaches has really good performance on their experiments, about 95% of accuracy, but then due to the use of inefficient metrics and end-to-end measurement, this is not applied in the real life. So this has very good results on the experiments, but in the real life, this is really not used. So it was goal for us. So we try to use this CICESE that first can work with just a few images. This generalized so well, and we also propose a kind of standard metrics that we think that are better that have been used than the ones that have been used until now. So first, the dataset that we use is a new one called Rabir that has 26 images, high quality images. This is the size of the images. And basically, it's the input that is the grayscale image, and the output that is a handmade mask of the vessels in grayscale. Also, this is going to be important later. And the architecture of the CICESE, let me go to this side. The architecture is basically composed of two different elements, one called generator and other one called discriminator. The generator tries to create the output from the input image as well as can be possible, and the discriminator tries to say, hey, this is the same or this is different. So this discriminator wants to discover if it is a fake image or it is the real image. So the whole architecture is a competence between the generator and the discriminator. So this is the main goal, is to minimize and maximize dependence of the generator or the discriminator. And the input of my whole network is going to be the real image, and the output is going to be the created mask, the generated mask. So we realized two different experiments. The first one, I'm going to go to this side. The first one is a simple one but powerful, and show different things that we want to we think that it's important to show. First one, we use just a few images, just 20 for the training, 3 for the validation, and 3 for the testing. And this is an important difference from previous paper because sometimes the testing dataset is forgetting. So they just use training and validation of training and testing. And it is so customized that then after we try to test this with a different images never seen before, this just doesn't work. So this is an important difference. And another important difference with this experiment is that with just 30 epochs, almost nothing talking in the world of the neural networks, we achieve an accuracy of 96%, which is comparable immediately with previous results. And I show here, I just discovered that I have a point. So I showed here the evolution of the iterations of the network. So for example, this is with one iteration, the output, pretty similar. This is 15 iterations, almost closer. And this is 30 iterations. That while it is not perfect, it's a good result that gets 96%. And here is another important question emerged, and it is this image is quite good, but it's not perfect. We can see that even with the small of the images, but this gets 96% of accuracy, and this is because of the metrics. So the standard metrics that are used are the same metrics that are used for all other problems of image recognition or that kind of problem. So we have accuracy, precision, recall, and F1 score. So what I want to show basically here is that, for example, in this case, precision, if this is my result, I have these two different images. I try this with my network, and the results are 96% of accuracy for this one, and 92% of accuracy for this one. So basically the metric is not working because it's the same for this image and for this image. And we can see also here the difference and how the metrics are not working for these images. Because, for example, for precision just measure how many of the pixels that are marked as vein is really a vein. So even if these are just a few one, if they are all correct, it's gonna be correct. So that's a wrong metric for this problem. So we can see here, for example, this is for the experiment A, and this is for the experiment B. We have two classes for background and blood vessels. And here in precision, all should be, in the experiment A should be high, and in the experiment B should be low, but all are kind of high, so it is incorrect. For recall and F1 score, we have more approximately good results here, because, for example, this should be high for this one and low for this case, and these represent what we want to achieve, but even they can fail at some cases. So I propose here different metrics that I propose also to be used for here onwards for these kind of problems of vessels, blood segmentation. What is the average Jacquard index that basically takes into account both classes, if it is background or it is vessel, and also, as these are good here, had good results, but not always are going to work for both classes. I propose to take the average. So I use these metrics, but with a different two experiments. And now I use also data augmentation to improve the accuracy. And the second experiment was almost the same that the previous one, but with data augmentation, approximately 1,000 images to train the model, split also into train, validation, and test data sets. And the results are pretty good. And next, we're going to see the metrics. And the other one with color images. So I artificially color the images to have difference entre vein and arteries, and could be able to help more in the diagnosis and treatments of different diseases. And it was also obtained good results. These are the results with the proposed metrics, and these are comparison with another models. So, talking about the comparisons with other models, this is using the pretty standard metrics, and we can see here our proposal, and is the best with this another approach that also use a kind of generative network. So these are going to be the best one here, but it could fail, right, because of the metrics as we saw before. So this is the result. These are the results with the new metrics, and these are pretty more related with the reality. So in conclusion, we successfully use this generative adversarial network to segment these retina vessels with a success of up to 90%, but for arteries and veins, no need pre-processing steps, because most of the previous papers have pre-processing steps. This one it's not required. Use a small data set that is pretty near what we found in the real life healthcare data sets. We propose different metrics that are more related to this problem, and we think that are going to work more or are going to work better in the future. It would be very interesting. Also, for this reason, in future works, propose now a whole end-to-end framework to test this kind of problem, and also have an evolution of this kind of neural network to be more customized to this problem, depending on the disease or something like that. And that's all. Thank you for your attention.
Okay, we have time for questions. Any question? Speaker? Okay, regarding the SIGAN that you use, the architecture of the SIGANs that you use, is those architectures are adopted from the literature, or did you design a particular SIGAN for your approach?
Yes. Great question. In this case, I use a well-known architecture for this kind of network that is called PCX. That is one I just mentioned briefly here. The architecture of the network. But if you want to reproduce my work, it's pretty easy. Just going to the paper, and it's well described how it is built.
And in the same sense, when you talk about the future work on evolving this SIGAN for other type of images or problems, what do you expect changes in the architecture of the SIGAN for other type of images?
Well, that's even a better question, I think. And also interesting, because now the evolution of this kind of neural networks have increased quite fast, super fast, I would say. So when I started this work, you can go to the literature and basically was just this one, but now there are like 30, 50, I don't know, different kind of networks. So first, we go to the literature, see what is evolving. Now we have transformers and different kind of things. And based on that, maybe a custom solution with this kind of problem would be the better approach. And also, I have so different another data sets that I would also wish to try.
Any question for speaker? Okay, thank you very much. Certificate to research. Thank you. Okay, we move on to the next presentation. Which is presented by Jose. Okay. The name of the talk is Evaluation of heat maps as an explicative method for classifying acute lymphoblastic leukemia cells.
Good afternoon, everyone. Thank you for staying present here. I'm going to present the work that made with Oliver Cesarreta, Raquel Díaz Hernández, Leopoldo Zamorano, and I. The objective of this work is evaluate the heat maps and a speculative method for classifying acute lymphoblastic leukemia cells. First, it's important to define three concepts that often confuse when I use first, what is interpretability? Is the ability to explain or provide meaning in terms that are understandable to a human being. And next, another concept is explainability. It's associated with the notion of explanation as interface between humans and maker decision. This is important, and this work is focused on this definition. And finally, transparency. What is transparency? A model is considered as transparent if it's understandable. Transparent models are divided usually in three categories. If the model is simulable, decomposable, and algorithmically transparent. Now, what is a heat map? In this case, a heat map isn't a represent of the relevance that is in what pixels is important for the convolutional neural network. For example, if I have an image input, the convolutional neural network process the image and obtain a prediction. Now, for explain the results, we use an algorithm after the training model, and the objective is use a decomposition function to to conserve the relevance for each pixel and make a color map. In this case, it's a new image that use a scale color scale. In this case, is often to use a scale color that promise blue to red. In this case, each color is defined as something. For example, for heat maps, in this case, the color blue is the pixel have a low or not relevance for the decision. And when I use a pixel in color red, is the highest relevance. So
The difference to make a different heat maps depends on the dysfunctions. Some authors propose a different functions to make the different heat maps. In this case, we use a library, Maximilian and his team collect a different methods to make heat maps. And in this case, present at this library because it's easier for us testing a different methods and generate a different heat maps. And in this case, I finally check the correlation between the different heat maps. Now, different authors working, we classify the leukemia cells. In this case, Jan and Ader use the same application in medicine, but Albir used another algorithm. In this case, is line algorithms to make heat map, but both isn't evaluated by experts. It's important to remember that when I use neural networks, artificial intelligence in medicine, it's necessarily working together with experts. So in this case, we want to evaluate our results with an expert. In this case, it's important or it's possible to use a method to make heat maps as support of evaluation of prediction in leukemia diagnostic cells. This is the problem that we want to solve. And for this work, we use this data set. In this case, we divide it in 3 categories. B cells category, T cells category, and healthy cells. This is the models that we use to pertain the model. DGG16, DGG19, MobileNet B1, ResNet 550. At the end of the training, we obtain 33 layers, 15 layers, 422, and finally 234. This is the parameters and the accuracy that obtained at the end. Remember, for this work is not important to improve the accuracy because we want to evaluate heat maps by experts. So apply these methods or this library with these models using these methods different to make the heat maps. We obtain results like this and use this the last 3 methods for evaluation because for us it's more important or affords more important information about the cells. Okay, how to make this evaluation? In this case, we 5 medical experts compare the morphological feature present in the original image according to their other experience and the information provided in the heat maps generated for the same image. The evaluation consists in a scale of 1 to 5, where 1 is equal information percentage of 0% to 20%, up to maximum of 5, which equals 81% to 100%. The experts assign a score of each heat maps. This depends the correlation between the characteristics presented on the original image with the characteristics present in the heat maps. Each of them evaluated a total 120 heat maps using 5 cells for each class, class B, class B, and healthy. For example, this is some examples. We present first model BGG19, the original image. In this case, the image of the image of the data set is without the background. It's only segmented the cells. So next present the heat maps according to, for example, the heat map A is using the method ARP, the method the image D, deep Taylor decomposition, and finally input gradient. And another important information is that in this case with MobileNet V1, for the method ERP method, we don't is not determined. And this is the results for the evaluations. In this case, for the type T cells, the major results is obtained when you use a model VG19, and the highest scores that are obtained using a method input gradient, in this case, the average is 2.699, and this is correlated with the characteristics information presented in the cells. It's according to 66%, and in total obtained 10.5 high score in different, but in this case 20. Remember that evaluate 120 heat maps and obtain the high level 10.5. For classify cells type B, in this case the best results is using the model ResNet 50. And again, the method generating heat maps is using input gradient. This is the average 2.45. It's according or related with the 19% morphological information present in the heat map. And finally, for classify normal type cells, we obtain the better results using the method deep Taylor decomposition. It's a little difference in comparison when you put the gradient. Remember, the LRP is not defined in this case. And finally, we want to know what is the best model to generate heat maps. In this case, comparing all models and the free type cells, the best model to generate heat maps is used, well, in this case, is for the input gradient. And this is the average, the equivalent to the morphological information present in the heat map, and the number of high score evaluated. And in this case, in this work, we want to measure the concept. Is we repeating one of the image or the cells, because we want to measure the consistency between the experts. In this case, this first evaluation, comparing with the second evaluation, the results are similar. As the results is the experts, the consistency by experts is very good. The discussions. According to evaluation made by experts, the heat maps that obtained using these methods and these models don't provide the ideal information. Why? Because it's necessary often to identify mark the MOO1 classes. For example, the shape of the cells, the area of the node field, and the number of black holes, and different characteristics that are present usually in leukemia cells. Is necessary present to classify if it's a health cells or cells with a leukemia category. So the conclusion of this work, in this case, using the method input gradient to generate heat maps is the better method to correlate. This is the better method that to correlate. Is the better method to provide information about the characteristics in the cells. But it's necessary to improve this information or these methods. And the future work is in important working together with the experts, evaluate new heat maps, using automatic feature extractions, and maybe it's a good idea to use semantic segmentations or identify a region of interest before to apply heat map methods to generate. So this is some reference. Thank you.
Okay, thank you. Time for questions. Any question? The speaker? Okay. Regarding the computational cost of the three methods that you applied, is there any significant difference that we need to consider besides the method that you use to determine its capabilities?
Thank you for your question. Yes, depends the method that you use. In this case, for example, if I use the method deep table decomposition, the time to generate this heat map, it's around 2-3 minutes per image, and contrast with another, for example, ERP or input gradient, it's around seconds. So depends. Well, in this case, for example, I think that an appendix. This is an example for the decomposition functions. In this case, only present the three methods that we use, and the algorithm is more complicated sometimes, and so this is the tool why the cost of that.
Any other question? The speaker?
Hello, one question. What do you think is most important for use explainability methods in healthcare?
Thank you. It's a good question. Because in a short answer is because we work with a live process, so it's important to know how to the artificial intelligence to obtain some results. In this case, artificial intelligence or evolutionary neural networks is in a heuristic results, so it's difficult to obtain how or it's difficult to know how to the artificial intelligence obtain the results. So we want to use another method, in this case algorithms, after to artificial intelligence to try explain the results. And finally, the experts take the last decision, but it's important to increase the explanation of the results.
Any other question? No? Okay. Please take the speaker.
Thank you.
Here, thank you, please. Okay. Time for the third presentation. Nombre es
Andrés
Andrés. Okay. Okay, the third presentation of this last session is CICESE method for multiple criteria decision making applied to trajectory selection for autonomous driving. And Andrés Arenas is presenting.
So, hello everybody. Sorry, I started what I'm presenting. It's called here. As mentioned, I skipped this part. So the contents for this talk are introduction, background, method, experiment results, conclusions, and future work. For last, reference. So autonomous driving systems aims to improve the safety of the passengers and the drivers around. Through path planning and trajectory selection, the objective is to avoid collisions. So we propose the use of multiple criteria decision-making methods such as the technique for order or preference by similarity to the ideal solution or TOPSIS to evaluate each trajectory toward an ideal solution. So the objective is to develop a method that plan and select optimal trajectories to prevent collisions, combining a path planner algorithm with a TOPSIS decision-making method that selects that trajectory. The proposal resides between the perception module and the control module of the autonomous vehicle. So here's some background. First, the path planning algorithm is a reference system. For this work, we use the frame and the polynomial to generate the trajectories. As we see in the figure number 2, we have the array of trajectories. So first, the generation of the frame is generated by the parametric cube of the ROAD. So the tangent vectors and normal vectors work as the axis of this reference frame. The tangent vector is the longitudinal motion axis, and the normal vector is the lateral motion axis. Then the effect of the polynomial is applied. This algorithm generates the trajectory that connects the initial states of the reference path with the end states or target states of that path, as we can see in the operations 3 and 4. With these expressions and the first and second derivatives, we obtain the speed and acceleration of the vehicle. Then for the estimation of the steering angle, we use the standing control model, from which obtain the expression 5 and the expanded version that contains the limits for the steering angle of the vehicle. And then, with all this information of the speed, acceleration, and steering angle, we apply the TOPSIS algorithm. This method takes the array of trajectories generated by the path planner algorithm and with two other parameters given by the user as the weight vector and impact vector. The weight vector contains the weight for each criteria that will be taken into account, and the impact vectors works as an indicator for the TOPSIS to stimulate the increase or decrease of each criteria. Then the first step is to normalize the array of trajectories through expression number 7. With that normalization, we translate the values of the array to a fuzzy domain. So then we apply the weight vector to all the values of the array. And then we compute the ideal best and ideal worst vectors that serves as the comparison to the ideal solution of the TOPSIS. So the ideal best is computed to max function in the case that we have the desire to increase certain criteria, or the mean function if we decide to decrease certain criteria. Then we apply the Euclidean distance to measure the difference to that vectors and estimate the positive distance and negative distance to the ideal solution. So with that distance, we proceed to compute the score with expression number 15. So the score is assigned to each individual trajectory and takes values from 0 to 1. With that values, the highest, so the closest to 1, is taken as a reference from the control medium. So in the next figure, we have the proposed polynomial TOPSIS. The process starts with the initial parameters, with the perception module that generates the parametric curve and the initial and end states. With that information, the path planning algorithm applies the first order polynomial and generates an array of trajectories that will be characterized in the dependent frame. With those trajectories, the trajectory selection releases in the experience transmission vectors of weight and impact vectors to select a trajectory. That trajectory, as mentioned previously, works as reference for the vehicle control module that carries the task of path tracking. So we can pass the experimental results. The metrics that we use for this research was efficiency as the average top speed of the vehicles, safety as the number of collisions that occur in the experiments. Besides this, we use the number of lane changing maneuvers to measure the performance and the off-roading cases. For comparison, the performance of proposal, we use the constraint driver method, CDM, collision checker, and a version of this same algorithm, but with unadjusted weight and impact vectors. So the first experiment involved a scenario with dynamic obstacles, other vehicles that travel around the ego vehicle, we can see in figure A, and with the respective reference path. The quantitative results for the experiment showed that the number of collisions were reduced and the average top speed increased because the impact vector was configured for the stimulate of the increase of that criteria. And the number of lane changing maneuvers were reduced in comparison with other methods, and off-roading cases, there is no cases of occurrence. So the increased speed given by the influence impact vectors can surpass the limit. We can see the limit for the experiments were 25 kilometers per hour and 10 kilometers per hour. We observed that the top speed for the adjusted topsies goes beyond this limit. On a straight road, the number of off-roading cases were reduced because the geometry of the road didn't difficult the functionality of the path planning algorithm. So the number of lane changing maneuvers was increased due to the interaction with the dynamic obstacles. Then we have another experiment. This experiment involved a winding rod. As you can see the figure 8 with their respective reference path. The number of collisions in this scenario was increasing, and the difficulty was increasing because of the existence of curves. The average top speed was reduced because the vehicle has to stop in certain moments of the experiment to take the curves. The number of lane changing maneuvers increased due to the change of lanes to take the curves, and off-roading cases just at the same tendency at the lane changing maneuvers. So the discussion for this experiment is that the presence of curves in the road generates more change maneuvers. These change maneuvers reduce the speed of the vehicle, and the topsies with adjusted vector of weight and impact shows the worst performance, reflecting the lack of variance transmitted to this algorithm. So the conclusions and future work. The conclusions are that a scheme based on the fifth-order polynomial and topsies was presented for path planning and selection of the optimal trajectory. The proposed approach generated an average increase of 30% in speed with 16.44 fewer maneuvers and 12.5% less collision compared to the other methods. And using decision-making methods such as topsies in the context of self-driving can lead to softer and more human-like behaviors. And as future work is contemplated, taking into account more specific criteria to enhance the performance of the proposal in curve or winding roads, explore methods for a better compression of the data generated by the path planning algorithm, and ensure that there is no loss of information. So we pass to our reference.
Okay, any question?
Thank you for the presentation. And actually, I have two questions. The first one is the time an issue? I mean, it looks like you need to perform a lot of computations. So, what if you have a path, and when you try to execute it, the path is occurring? And the second one is, what kind of sensor are you using to see the environment? Thank you.
Okay, thanks for your questions. First one. Well, for the time of computing, the proposal, so the technique of autopsies, was it's a very simple method, as we can see in the and with the span. The number of operations that needs to be made to select a trajectory, the normalization, apply the weight, estimate the ideal best and the worst, and can estimate the distance. The score is a simple, it's the formula. So the time that this algorithm requires is milliseconds. In the case of the path is occurred by another vehicle, that will be a problem carried by the perception model that has to be enhanced to detect the vehicles around or more distance. And then led to the second question that was in these experiments we don't contemplate the perception model, just the path planning and selection of the trajectories. So there is no sensors.
Okay, thank you. Any other question?
Thanks. My question is related to the weights. Is this algorithm more human-like because of the weights, or perhaps miss the part? How are they selected? How do you choose the weights of this algorithm? Thanks.
Yes, that was the key part of this, so the human leg. The weight and impact vector were defined by experienced divers that estimates the importance of the velocity, speed and acceleration and steering angle of the vehicle. So we have a fuzzy system in the fuzzy domain with an inference system of weight in the vector of weight and impact.
So it is a transfer of knowledge, right?
Of experience. Experience.
Any other question? Okay, thank you very much. It's the fourth talk of this session, presented by Ms. Valentin Coronado. The name of the talk is Machine Learning Based Estimation of the Bending Magnitude Sensed by a Fiber Optic Device.
Okay, well, thank you. Good afternoon. Well, I want to talk about a little bit of what we are doing with machine learning and some optic devices. So first of all, bending measurement is a highly issue of some engineering problems. Why? Well, because bending measurements can be useful for measure something like the wings, the formation of airplanes, or even to see the health of beams and columns, or also to determine the position of a robotic arm. So this kind of phenomenon can be measured with, well, commonly are measured with strain gauges and accelerometers. This one is a strain gauge, and this one is an accelerometer. And nevertheless, in recent years, some other kind of sensors, like the optical fibers, have been used to measure also this bending. So why? Well, because it has some advantages. For instance, this kind of sensors, I mean the optic devices, are light, high sensitive, have good repeatability, and also are electromagnetic and electrical means to the environment, and can be implemented in industrial environments, which are very broad. So I think the question could be how this kind of sensors works. Well, this is the general setup that this type of devices have. And here we have 4 principal elements. The first one is a broadband source. Also, we have something that is called a circulator, a digital oscilloscope, and of course, fiber optic. And the way that it works is the following. The broadband emits light, which goes to this circulator. Then the light travels until it reaches the tip of the fiber. Then some of the light is reflected, and then the oscilloscope shows the sight that we get after this light has been reflected. So, bending monitoring implies accurate interference detection of the signal, like this one, and then we can track a point, for instance, a minimum of this signal, and this tracking helps us to see the magnitude of the bending. This could be easy, but we have some problems. For instance, the range of the bending monitoring will be limited, and also the direction can become difficult to identify. But given that these kind of sensors have high repeatability, we are able to use a machine learning techniques to estimate the bending magnitude. Then we build an experimental setup that, of course, have all the elements that are already mentioned. But in this case, as you can see, we have the 4 elements, but we have here 2 special things. The first one is that we have something that is called a single mode fiber optic and a multi-mode fiber optic. This means that the way that the light travels will change. And also we need to couple these 2 fibers in some point. So as you can see here in this blue box, that the light go from this point to this, and then the path that the light follows is split. Then when it's reflected, the light is coupled again, and it produces this signal, which is called an interferon. Okay, we have the specific instances that we are using for this broadband. And well, once that we have this sensor, we do the following. We place the fiber optic, in this case this line in red, around this rod, which is fixed in this position and is free in this other position. Then we apply a force, in this case is F, and we produce this bend. For these experiments, which is a proof of concept, we are using 3 different positions, which are called P's of I, where I is 1, 2, or 3. And we also have 8 different angles for each of the position of this line. Well, of course, we have to repeat this bending several times in order to have enough data to build our classifier. And well, this is the general approach or pipeline that we are using, which is a supervised classification approach, which is very common. So we need to build our database and then split the data into testing and training. And we are not using the raw signal. Instead, we are extract some characteristics from this signal, which is also common. In particular, we have using 26 descriptive features. For instance, including the mean, the maximum, the mean of the signal, the median, among others. So then we use all these features and map them into a feature vector, so, which is very common. After that, we are using 4 classical machine learning algorithms, which including super vector machines, k-nearest neighbor, naive Bayes, and random forest. Why these 4? Well, because they show good performance in task for in the classification task. The overall workflow strategy is summarized in this algorithm number 1. We have the raw signal, then we extract all the features. Of course, we have to label these features. These vectors that include the features. Then we split this data into training and testing, and then we train all the 4 models. And finally, well, we evaluate its performance and we compare among them. What we have, well, as you can see here, we use the accuracy, precision, wrinkle, and F1 metrics, the common metrics that are used for classification. And the best model was the random forest, which is in red, for all the metrics, followed by the super vector machines. And the worst model was the naive Bayes. As you can see, we get 100% of classification, which could be weird, but given the repeatability of these kind of signals, it's normal that this behavior appears. Besides, to achieve a more statistical, reliable estimate of the performance of each model, we run a tenfold cross validation, and here at the left, you can see the box plots of after the tenfold cross validation of the accuracy metrics. And again, the best one is the random forest, and the second best one is super vector machines. In the right side, well, you can see the mean value of this accuracy, of the accuracy metric, for the tenfold cross validation. Well, with this, we conclude that the random forest is the best option to use this kind of signals. But if the time is an issue, we are talking about milliseconds, but we need to see that the random forest is almost around 8 times slower than the super vector machine. And the super vector machine, according to the experimental results, we see that it's also an option. So if you need spend less time, you can use super vector machines. But if the training time is not an issue, well, use random forest. Okay. Well, finally, as a conclusions, this work, a machine learning methods for estimating bend magnitude have been proposed. 4 machine learning models were implemented and compared. The proposed method performs very well, specifically at random forest. And well, we see that the super vector machines is a good option also to do this kind of task. And in summary, this proposed method is an efficient alternative to be used for estimating bend magnitude. Well, there are some references for this presentation, and I'm very happy to answer questions there.
Okay, Any question for the speaker? Okay, I have one question about the parameters of the classifiers that didn't work well. For example, KNN is very sensitive to the K value, for example, or the SVM. If you vary the kernel of the approach and to try to improve them by means of the parameters.
Okay, thank you. Yes. One of the things that makes the random forest slower is that parameters. We need more to reach these classification numbers. And we tried some, but in all cases random forest was the best one. In the case of support vector machines, we use the linear kernel. We don't have enough time to try another kernel, but we see that the random forest works very well, so we think that we don't really have them. In the case of the other models, well, this is some shallow learning models that we know that they are not really good enough as the other ones, so we don't change too much that parameters.
Thank you. Any other comment or question for the speaker?
Hello. First, congratulations with your work and cool presentation. Congratulations.
Thank you.
Two questions. First, what is the ultimate goal or the purpose of measure line magnitude? And second one, do you think that could be important for future work? Include some noise on the input to see how it behaves under that circumstances.
Thank you for your question. Yeah, we want to do something like this at the end of this project. Something like this. And also, we start with this as a proof of concept, but what we really want to do is to see the shape, not only the magnitude of the bend, but also how this, for instance, this column looks like. So we are working on that right now, and we need to obtain more data. It's difficult for this type of structures because you have to build them and then bend them. We are building a small prototype to reproduce this kind of phenomenon. And at the end, we want to put it into real life scenarios. Right now, this works in laboratory because there are some issues. For instance, this element is very expensive, and this one could not be used out of the laboratory. So we have to change this for a photo gap, and then we will try to use another technique which is similar, but we don't have in that case the complete signal, this one. Instead, we have just a window, so we have to see how to handle this problem.
Any other question? Okay, we thank the speaker. Hello, can you hear me? So we can see you, but we can't hear you. We can see you, but we can't hear you.
Can you hear me? Can you see me?
Uh, yes, we can hear you.
Okay, I'm going to increase the sound. So I'm going to share my screen.
Uh,
And
yeah.
can you see my screen?
Okay. I think it's coming. Yes. Wait a second.
Can you see my screen?
Not yet. Now we can see your screen.
Okay, good. All right, shall I start?
Uh, wait a minute, please. Mhm. Can you please start talking, please? We are checking the volume here in the room.
Okay. So good,
Yeah, we can hear
good
you.
afternoon, everyone.
You have 15 minutes, please. 15 minutes.
Sorry.
15 minutes for your presentation.
Okay. All right. I'm going wait. I'm going to turn off my the sound here, and I will just talk. So using the mic, so I don't have the sound coming back. So good afternoon, everyone. So I'm presenting a title entitled Graph-Based Semi-Supervised Learning using Riemann and Geometry Distance for Motor Imagery Classification. It's a paper about brain-computer interface. So the authors are myself and Eric Smorsky. So we are from the Department of Computer Science at California State University, Fresno, Hispanic Serving Institution. So for the introduction, so the application, as I mentioned, so brain-computer interface, where the main challenge is not just to detect brain responses, but to have real application that we can leave the lab and that can be used by disabled people, by old people, so in clinical settings, in retirement home. So leaving the lab is extremely difficult, and we have to leave the classical paradigm of supervised learning, where we have a calibration session, and after we move towards the deployment of the system using simply a calibration session, and we just hope that the system is going to work. Unfortunately, that's not going to be the case for brain-computer interface. So we have some very big problems in terms of the EEG signal instead of the non-stationarity of the EEG signal. So there is a need to recalibrate over time quite regularly. So you just use the EEG cap, you change the EEG cap, you get used to the task. So there are lots of issues where just relying on supervised learning, so using calibration data, is not going to be enough. So we can deal with this issue while still staying supervised learning by learning with a large data set, so from a single user or learning from a large group of users. and trying to catch the underlying distribution of the brain responses that you're trying to detect, but that remains quite difficult, and it's better to track the problems, or at least to learn in unsupervised way or semi-supervised way what's happening over time. So here the issue is focusing on motor imagery detection, so using event synchronization, desynchronization, so the type of brainwave that you're trying to detect. So typically it appears in the mu band between 8 and 12 Hz and the beta band between 12 and 30 Hz. In the literature, different approaches have been used, so using different frequency bands, so between 8 and 30 Hz. So we have approaches based on discriminant approaches, so using common spatial patterns, so a type of spatial filter. Then after we use some log bar features, the log of the variance of the signal. And then after, typically, we continue with linear discriminant analysis classifier with simple vector machine, so state-of-the-art classifiers. Another way so to use deep learning, so by using some particular architectures for convolutional neural networks. And one approach that has been recently used, I mean, in the last 10 years, but still not widely used, I mean, going back to density-based approaches, where the main point is to use a really good distance, really good features, and then so we can use k-nearest neighbor, distance to the mean classifier that can be quite efficient. So it allows you to consider how the data is going to change over time, and then to adapt. So motivation for brain-computer interface, as I mentioned in the introduction, the main challenge is really to how we go from the lab, how do we go from research papers, and after we can transfer and to get clinical and commercial applications. So that's really a big problem. So we need to decrease the calibration session for BCI and to adapt over time. So per trial, so after every trial, we're going to modify the system, so depending on what we obtain, or per block. So per block, so as what we're proposing here, so we have unlabeled examples, and we're going to consider these unlabeled examples in order to in order to take advantage of the data. So just oops, not to make sure there are no okay. It's like this. Slideshow. Sorry about that. So we're using semi-supervised learning, so considering undirected graphs. So for such a problem, so we need to determine the affinity matrix. Determining the affinity matrix is really the most important part in the problem. And then so afterwards, so we can use state-of-the-art approaches. So in order to build a very good affinity matrix, then we need to use a good distance, an appropriate distance in relation to the problem. The focus of the paper, so contribution number 1, so we perform label propagation at different steps, different stages, instead of just applying label propagation just one time. So we consider different affinity matrices based on, so contribution number 2, so is a comparison of neighborhoods of different sizes, and also on distances, so different distances, in such a way that each time when we're going to increase the number of neighbors in the affinity matrix, then it is based on the distances between neighbors. So finally, contribution number 3, so it's to assess this type of approach, so using the Riemann geometry framework. So Riemann geometry framework that I'm going to explain afterwards. So finally, so once we have a good affinity matrix, then we can perform the label propagation. So label propagation is going to propagate examples that are labeled to unlabeled examples. And after, for all the unlabeled examples that have been labeled, so they can be used, so 2 ways. So one, to retrain the system, to recalibrate the system, and we assume that we need to properly label these unlabeled examples to have a high quality classifier, so that's the main assumption. Or if we can go back in time and take advantage of the label of this unlabeled example, then we can still use, work on the output of the classifiers. So self-supervised learning using the graphs. so in relation to spectral clustering. So we need a very good affinity matrix. So if the label propagation is performed with a graph where the connections do not allow to cross all the different vertices in the graph, then label propagation is not going to be able to propagate everywhere. If it's too large, then label propagation can go through bridges with mislabeled examples. So instead, so we perform multiple iterations. So we want label propagation to converge at different steps in such a way that we are safe in the way we progress throughout the labeling of the complete datasets. So we run label propagation at different stages. So it's also one way to decrease the number of parameters that we need to set in the system. So how many neighbors we need to consider, what's the ideal distance that we need to consider from one vertex to other vertices to make sure that all the vertices belong to the same neighborhood. So unless you're going to have, again, I mean, a calibration session and then define the purpose of adding unlabeled example, then we cannot set these different parameters because all the different users, different participants, so in these EEG studies, so they are unique. So it's very important to reduce as much as possible the number of parameters that we need and just go well with what we can. So that's why we increase we change over time through different iterations, so the number of neighbors or the distance from one vertex to other vertex, from one neighbor to other examples. So requirements, which is very important, and that's why we're going to use the Riemann geometry framework, so to compute the distance between two examples. So state-of-the-art assumption, so smoothness assumption, so if 2 points are x1, x2 are in a high density region, so if they are close, then the output, the labels, so should be the same. A cluster assumption, so if you're going to have multiple examples that are going to be in the same cluster, they're going to share the same label. And the manifold assumption, also very important. So the data, the high dimensional data, so it lies roughly in a low dimensional manifold. So we really need an efficient distance to compare these examples. So if two examples are close, they're going to share the same label, and using an efficient distance, the label propagation is going to have some good results. So as an input, so we consider the covariance matrices. So we have a matrix of size, number of sensors by number of sensors, so in relation to the EEG signal that is recorded. And for each trial, we have this covariance matrix, so from a particular time segment that we consider, so 2 or 3 seconds. Covariance matrix meaning we're dealing with symmetric positive definite matrices. Therefore, we're dealing also with eigenvalues that are all positive real numbers, and therefore we can use the Riemannian geometry framework. So here we want to be in a space where computing the distances, so we are on the right definition of the space. So using the Riemann, for this particular type of input, and very important that it works only with these covariance matrices. I mean, they need to be SPD matrices, otherwise it doesn't work. Then we can use these properties. Now, for the classifier, so we can use distance to the mean for each class, the nearest neighbor, and here we're proposing to use the semi-supervised learning with label propagation. So here, well, on the side, so here we have the pseudocode for the label propagation, which is quite simple. I mean, that's one brick of the whole system. Very important, so is to have the appropriate affinity matrix that is computed, so using the Riemann geometry framework, so to assess the distances, and also this label propagation algorithm, so is run multiple times until all the different examples in the dataset of unlabeled examples are all labeled. So the evaluation of the approach has been performed on a dataset containing 14 participants. So we have sensors that are placed around the area, so where we expect to find motor imagery, so C3, CZ, C4, so central area on an EEG cap, sampling rate 512 Hz. And for the time segments, as I mentioned before, so we're considering 3 seconds. Bandpass, so we consider the mu and the beta bands, and then we have for the different training and test trials, so we get everything all together. And for the train and the test evaluation, So we check. So and so we have the figures in the paper. I mean that are in the next slides. So in relation to the number of labeled examples, the number of unlabeled examples, so what the trend, so how we can decide, so how many examples we can have until when the performance is going to really drop, when you have not enough labeled examples in order to propagate the labels to the unlabeled examples. So for the experimental conditions, so we consider so two cases. So for the algorithm, so by considering the number of neighbors in the graph that's going to evolve, so from one neighbor to, so how many, I mean, the maximum number of neighbors that you need in order to propagate, label propagate to all the example in the graph. And also for the distances, where you increase the distance, so we start with a distance corresponding to the mean distance from one example to another example, and then we increase each time, so in order to add additional elements, additional examples into the neighborhood in the graph. So very important step, but I really want to stress. So the signal is first filtered, so using a geodesic filter, so based on the Riemann geometry. So that's a very, very important step before moving forward, so using the distances. So we really want to be first in the right space before using the distances. Now we compare three distances, so the Riemannian distance, the Euclidean distance, and the Euclidean distance with the z-score. So here we have the evolution of the accuracy and the number of iterations, so in relation to the ratio between the labeled examples, the unlabeled examples. So as you can see, so after, well, if you just use, so 10% of the label examples, so here we have some drop. Now you can see that even, I mean, the envelope that you can see in the graph, so it corresponds to the cross-validation. So we have the gap across the different folds for the cross-validation, and the line in the middle corresponds to the mean across the different folds. So for the cross-validation, for the different blocks that we are considering. So you can see between the Riemann geometry, Euclidean, so Euclidean discourse, we have the same trend where after, so yeah, 10%, so we have a drop, and then also we have some variation. So, but overall, so it's quite stable. So throughout the different splits between labeled, unlabeled examples. So what is used for training? I mean, yeah, as retrieving the labels and unlabeled examples. The same trend is observed so when you use the distances. So here, as you can see, however, so the drop is more severe when you reduce the number of labeled examples. So and the trend is similar across the three distances. Now, when you arrive to the evaluation, I mean, just focusing, I mean, you can look at all the different possible splits. So here we just focus on the one is the 50%, and for 50%, so in this case, so for the analysis, so the best performance was observed with the approach with the distances, where we get across the different participants, so 73%, so compared to around 71 for the other elements. So between the different distances, so very, very similar results. So because we use so the geodesic filter, so across the distances, there are not many big differences. So the graph stays stable so after all the different processing steps. So that's important so to notice here. And also for the results, I mean, I know depending on the applications, we may be more familiar with, I mean, high accuracy, 90% and so on, but motor imagery, so it's important to tell that it's a difficult problem. You're going to have some participants that they're good and they are able to evoke these brain responses. I mean, they're able to properly think about moving the left hand, moving the right hand, and so on. While for other participants, then the results are going to be quite poor. I mean, you can see, so subject 13, 14, so we are close to 50%, so it's quite low. However, for some others, the result can be quite high, yes, close to 100%. So discussion. So to conclude, the affinity matrix, so that's really the most important part. And then we want to decrease the number of parameters. So we have assessed so two approaches. So one based on the increase of the distances, so to create different affinity matrices. The other one with an increase of the number of neighbors. And assessing the BCI performance remained a challenge, in particular for this case, we went to focus on the effects of non-stationarity, or if the EG signal changes, how it is possible to consider unlabeled examples and based on the labeled examples to properly propagate, so to those that are close, because it is, I mean, the EG signal has some non-stationary properties, but it's not like it's going to go from one state to another state completely. So we have a smooth change. I mean, unless we go from very complete session to a different session, or we want to do the shift, the coverage shift happening from one participant to another participant, where the shift is going to be more severe. So, conclusion, BCI based on motor imagery, so it's a difficult problem. It has strong variation across participants. As a pattern recognition problem, so it has to move away from just supervised learning. You have challenges the calibration session. You have to deal with non-stationary properties of the EG signal. And also a difficult experimental task for the user. So the label of the different examples that you have, we're not even sure that they really correspond to the type of brain responses that we have in the signal. So to finish, I want to stress also that for large dataset, large graphs, so we need also efficient data structures, because the size of these affinity matrices can become quite large. I mean, if it has to work in clinical settings, so if you deal with a lot of examples. So thank you for your attention. Contact information, so that's me, so TSU Fresno. The code was implemented with MATLAB. If you have questions, if there is some opportunities for collaborations, so please do not hesitate to contact me. I am happy to share the code, share, I mean, explain so how I got the data, I mean, data obtained from BNCI Horizon 2020 projects. There's lots of data sets, and then to discuss any questions. So I will reshare, get back on, get the sound on, so there's no. Do you have any questions?
Okay, thank you. Thank you for the presentation. Is there any question for the presenter?
I know it is online, so maybe you can just send me an email. Send me an email. I will be happy to reply, or even to meet on Zoom or with any of you.
Okay, okay. I think it's the best because we can hear you clearly. So thank you for the presentation.
All right, so.
Thank you. Bye-bye.
Sure.
Thank you.
Hola. 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 Ahora sí. Bueno, pues como decía, todo lo que comienza, pues un día tristemente pues, termina ya. En particular el MCPR pues no termina acá. Vamos a ver al final que sí va a continuar, pero el MCPR 2023 pues ya le está llegando a sus últimas horas. Y digo está llegando porque mañana tenemos tutoriales, los tutoriales número 1, como el del doctor Efraín Sura acá, y el tutorial del doctor Fabio González, que va a ser en el CICESE, en la instalación del CICESE. Pues llegado el momento de clausurar el evento, vamos. Pues haciendo un resumen de este evento, los organizadores principales de este evento fueron el Centro de Investigación Científica y Educación Superior de Ensenada, Baja California, en su unidad de Conferencia Tecnológica TEPIC, CICESE 3. Tuvimos la sesión del miércoles en la tarde, donde se va a hacer uno de los tutoriales mañana. El Centro Naderita de Innovación y Transferencia Tecnológica, que es acá donde estamos. Muchísimas gracias al doctor Julio por aceptar, prestarnos este espacio y colaborar con nosotros en la realización de este evento. Muchísimas gracias por todo el apoyo de no solo usted, sino de todo el personal ¿ya? Y del Instituto Nacional de Astrofísica, Óptica y Electrónica. Y en primer lugar, pues ya antes de esta sesión, esta edición del MCPR 2023, pues ya había logrado crear un congreso con 14 ediciones anteriores y que han ido llevando de la mano, y este año pues nos dieron la oportunidad de traer acá a Tepic pues un evento de esta magnitud. Cuando digo magnitud no me refiero a cantidad, porque es un evento donde no somos tantos, pero si hacemos muchos, hacemos comunidad, y espero que hayan podido aprovechar y hayan podido disfrutar las conferencias y los espacios que preparamos para que pudieran entre todos interrelacionarse, ¿no? Y bueno, continuamos. En este congreso tuvimos 3 invitados especiales para impartirnos conferencias magistrales. El doctor Fabio González, un aplauso para el doctor. Muchísimas gracias, doctor, por haber aceptado nuestra petición de venir acá, haber viajado desde Colombia hasta acá para compartir con nosotros sus conocimientos. Por otro lado está el doctor Cafri Carray, quien nos dio una conferencia de forma virtual. El doctor Carray trabaja en un centro de investigación en Canadá, estaba de sabático por allá en Arabia Saudita, y aún así pues dijo, no se preocupen, yo les imparto la conferencia, no voy a poder ir por temas de salud, los viajes son muy largos, pero seguro que los acompaño y voy a estar desde allá, ¿no? Entonces ese es el otro el conferencista magistral. Y finalmente, pues, el doctor Efraín Mesura, ¿dónde está? Se me perdió por acá. El doctor Efraín Mesura, quien también nos impartió una conferencia magistral desde acá, desde México. Como digo, tuvimos 2 keynotes extranjeros, un keynote mexicano, que además nos va a hacer un anuncio. Terminando yo de hablar, le voy a dar la palabra. Bueno, es importante señalar que el MCPR no solo trajo a investigadores y estudiantes mexicanos, sino también de diferentes partes del mundo. Hubo 61 artículos enviados de 12 países, y entre estos países, además de México, estuvo Bélgica, Canadá, Colombia, Cuba, Ecuador, India, México, bueno, ya decía México, Pakistán, Sudáfrica, España, Estados Unidos y soy malo con los nombres de los países entre español e inglés, Irlanda, ahí ando medio un poquito perdido en ese punto. Bueno, hubo 30 papers aceptados de esos 61, 50%, un poquito menos, y que aparecieron en el volumen Pattern Recognition de la Lecture Note in Computer Science, es publicado por la Springer, ¿no? Desde la página web del evento pueden los autores durante todo un mes descargar el libro en formato PDF. Y bueno, si alguno no lo puede sacar en ese tiempo y lo necesita, pues nos lo pide y nosotros con gusto se los haremos llegar. Por otro lado, bueno, aquí está, esta es la liga, ¿sí? Aquí tenemos la liga, ¿sí? Pero entrando en la página van a ver que está el ebook en la página principal y ahí lo pueden descargar. Por otro lado, este evento, el MCPR tradicionalmente tiene 2 premios, el Best Paper Award y el Best Paper Award de la MCPR y APR, y el Best Paper Award para estudiantes también de la MCPR y APR. La IAPR, por si algunos de los más nuevos en estos congresos, de los estudiantes que nos acompañan, es la Asociación Internacional de Reconocimiento de Patrones. Y los ganadores de estos premios los vamos a anunciar en la cena hoy en la noche. Por otro lado, adicionalmente, esos papers que van a ser anunciados en la noche como ganadores de ambos premios, se les va a dar la oportunidad, van a ser invitados a que salga una publicación de su trabajo en la revista Pattern Recognition Levels. Sí es importante mencionar que hay que hacerle una extensión a los trabajos de un 40% o más del contenido que tiene actualmente. Si no, pues no se puede publicar como política. Y además de eso, por ahí, como siempre, los MCPR tienen una reunión de estudiantes. En este caso, yo creo que fue un gran logro después de la parte de haber tenido la pandemia, pues que hayan llegado con nosotros 3 estudiantes, hayan enviado y se han sido aceptados sus trabajos para presentar en póster. Gracias por confiar en el MCPR en esta versión. Lo mismo digo a esos 61 trabajos que se enviaron a la conferencia principal y de los cuales fueron seleccionados 30. Muchísimas gracias por estar acá, por haber enviado los trabajos y luego los aceptados, pues, por estar acá. Igualmente va a haber hay un premio para el mejor póster que también va a ser anunciado en la cena de hoy en la noche, que va a ser en el Hotel Fray Junípero, donde muchos de ustedes están hospedados. Y bueno, adicionalmente, comentar que todos los trabajos presentados en el MCPR 2023, los 30 trabajos, los 30 trabajos, los invitamos a que hagan una extensión del 40% del material de esos trabajos para que sean considerados y enviados a un número especial en la revista Computación y Sistema, y la información más detallada sobre este número les estará llegando por correo a todos los autores. Bueno, y finalmente, pues muchísimas gracias a todos por todo el tiempo dedicado en esta conferencia, por haber estado con nosotros en esta edición número 15, pero primera edición nuevamente viéndonos cara a cara, acá en un espacio físico, no un espacio virtual. La pandemia nos llevó a movernos al espacio virtual, y creo que las respuestas, se los agradezco muchísimo a todos los autores, a los keynotes que también nos impartieron los tutoriales, a los estudiantes que confiaron en enviar sus pósters. Pues muchísimas gracias por confiar en este congreso. Pues la conferencia iba a ser un éxito y participar con nosotros. Espero que hayan disfrutado muchísimo el congreso, espero que hayan disfrutado en particular toda la parte académica, pero como les decía ayer a los chicos que se quedaron conmigo hasta tarde, eran casi las 10 de la noche, estábamos ahí todavía esperando al segundo autobús, a la segunda vuelta del autobús nos llevara. Pues yo creo que ha sido un congreso que, más allá de la parte académica, creo que les haya quedado grabado a cada uno de los autores, sobre todo por esa parte de la interacción, de hacer comunidad, de conocerse. Ayer eran 8 o 9 estudiantes, 2 solo eran del mismo estado, todos los demás eran de estados diferentes, y parecía que se conocían desde siempre, ¿no? Entonces eso yo creo que es muy importante, que lo logremos armar esas redes en este tipo de congresos. Bueno, gracias por confiar en nosotros y por acá participar. Entonces, sentido general, ya lo decía, gracias a todos por hacer posible este MCPR 2023. Un aplauso para todos nosotros. Y antes de terminar, también quería agradecer a todas las personas que, aún sin ser miembros oficiales del comité organizador, nos ayudaron para que este evento fuera posible. A todo el personal de CENIT, ya a todo el personal de CICESE UT3, que ya vieron que es un centro pequeño, no somos tantos, y todos esta semana estuvimos acá trabajando, ¿no? Nombres que a lo mejor nos recuerdan o no vieron, estaban detrás de todo lo que estaba sucediendo. Entonces, pues gracias a todos nuevamente, y le doy la palabra al doctor Efraín Mesura, que tiene un anuncio para nosotros.
Muchas gracias, doctor Ansel. Buenas tardes a todos. Pues bueno, no sé si ya es sorpresa o ya no, pero el MCPR, estamos muy contentos que nos hayan dado la oportunidad de organizarlo en Jalapa. Entonces, el próximo año nos vamos a ver, siguiente por favor, en la capital del estado de Veracruz. Brevemente, llegar a Jalapa no es tan complicado. El aeropuerto más cercano está en el puerto de Veracruz, y del puerto de Veracruz a Jalapa es 1 hora en automóvil, 1 hora 10, 1 hora 15, en transporte 1 hora y media. Y de Ciudad de México a Jalapa pues hay muchas opciones de autobús, 4 horas y media más o menos tarda el autobús en llegar a Jalapa, pero es muy fácil llegar. Y bueno, pondremos ahí también algunas otras opciones para algunos colegas que vayan a algunas otras ciudades. Siguiente, por favor. La ciudad de Jalapa es una ciudad que está en cerros, tiene un clima muy particular porque estamos muy cerca de la montaña, pero estamos a 1 hora de la playa. Entonces, tenemos esa combinación de clima. Todas las personas que nacemos en Jalapa, primero que nos regalan un paraguas, porque no sabemos qué día va a llover. Podemos tener varios climas el mismo día, entonces pues les sugiero por ahí que se lleven sus paraguas. En Jalapa uno sabe que puede haber mucho calor, puede haber fresco, puede haber viento, ¿sí? Por la situación en donde se encuentra. No sé si le puedes dar clic ahí, no, necesito que le des clic, ¿vale? No sé cómo darle clic. Ahí donde está la de Jalapa, antes de eso. Te doy un videito, a ver si se conecta. Te debe abrir un navegador y a ver si me puedes subir un volumen. Ese. Hay que subir, bueno, sí, pues pausa para que nos vean. Y perfecto, como en silencio. Bueno, una probadita de la ciudad de Jalapa, mucha cultura, hay deporte, hay buena comida, hay buen café. Entonces, se va a poner muy bien. Siguiente, por favor. La sede es la Universidad Veracruzana, que tiene presencia en todo el estado de Veracruz, desde el norte hasta el sur. Nosotros estamos ubicados en el campus en la ciudad de Jalapa, que es el más grande de la universidad. Siguiente, por favor. Y estamos ubicados en el campus sur de la universidad. Ahí está la zona principal, el Instituto de Investigaciones en Inteligencia Artificial está en el campus sur. Siguiente, por favor. Y ahí están nuestras instalaciones, que son pues nuevas, en poco tiempo que las estamos ocupando. Siguiente, por favor. Ahí los vamos a recibir con mucho gusto. Siguiente, por favor. Ese es todo el campus sur. Siguiente. Como les decía yo en la plática de hace rato, pues nosotros somos el grupo de investigación de COVNECAP. Y bueno, este es el pequeño grupo de trabajo que nos va a recibir con mucho gusto en Jalapa. Han dejado la vara muy alta, entonces tenemos mucho trabajo que hacer para poder cumplir con las expectativas de organizar el MCPR. Y bueno, pues agradecemos la oportunidad, le damos las gracias a TEPIC y pues nos vemos pronto en Jalapa. Muchas gracias.
Bueno, y ya para terminar, porque sé que todos quieren ir al lunch, ¿no? Ya bastante tardecito, y los que no son de acá, pues más todavía, porque veo la diferencia. Seguro que está cogiendo la panza cuando hay uno por ahí. Me gustaría primeramente darle la palabra a profesor Tara, que es alguno de los miembros de acá de la presidencia, de los organizadores de este evento pues quiere comentar algo, pues adelante. ¿Alguien quiere comentar algo? Los directores de nuestros centros apoyaron.
Gracias, Ansel. Voy a ser muy breve porque sí ya se hambre. Pues nada más agradecer a todos por su asistencia y ojalá que hayan disfrutado de este evento y más allá de la parte académica, que por supuesto es la principal, pues que también les haya gustado un poco lo que hayan visto de la ciudad de Tepic. Los que fueron a los tours, por ahí me contaron que tuvieron muy buena tarde ayer, se salvaron de los que quedan, me han dicho por ahí, que esa un poco rara por acá, pero me da gusto, ¿no? que hayan podido disfrutar una pequeña muestra de lo que tenemos por aquí en Nayarit. De Tepic, pues vieron también un poquito de la Zitácua. Yo creo que estuvo bien el tour, espero que lo hayan disfrutado bastante y sobre todo que hayan establecido buenas relaciones, ¿no? Para lo que comentaba Ansel, pues yo creo que el objetivo de estos encuentros, sobre todo ya una vez pasada la pandemia y que sean cara a cara, pues justamente es eso, ¿no? Establecer este tipo de colaboraciones entre estudiantes de diferentes partes del país, incluso de fuera. Y pues nada, simplemente agradecer nuevamente al doctor Julio, a su equipo, al equipo de CICESE, que estuvieron apoyando en todo momento desde antes del inicio hasta ahora y mañana, que todavía quedan los tutoriales. Y pues nada más, ¿no? Entonces, gracias y pues espero que se encuentren nuevamente en Jalapa.
Pues buenas tardes. Simplemente reiterar que este Centro de Innovación, Transferencia y Tecnología es su casa. Creo que conocieron un poco de lo que hacemos acá en el CENIT, pero nuestra página está en internet, así con ese nombre CENIT, pueden ustedes revisarla, pueden comentarlo con sus conocidos, con sus enlaces, con sus pares. Acá se hace transferencia, tecnología, innovación en diversas áreas que tiene como prioridad el Estado. Agradezco mucho la confianza que CICESE ha puesto en el centro para ser sede de este evento. Evidentemente, al doctor Juan Martínez, gracias por la amistad primero que tenemos en este espacio donde convivimos todos los días, pero además al doctor Hansel por pensar que aquí podría ser una sede donde ustedes podrían vivir y aprender y comentar lo que aquí se hace sobre patrones en el país, ¿no? Al NAOE también su agradecimiento por el acompañamiento. Nosotros contentos siempre de recibirlos acá en la Universidad Autónoma de Nayarit, en el CENIT, en Tepic, en Nayarit mismo, y ojalá que les haya gustado tanto el evento académico como la parte social que tenemos en el Estado, y que vengan pronto a visitarnos en un ambiente más relajado, más de conocer todo lo que nuestro Estado tiene como bellezas naturales. Todo, tenemos playa, tenemos sierra, tenemos montaña, tenemos todo, y se come bien rico acá. Entonces, qué bueno que estuvieron aquí, me da mucho gusto que hayan podido asistir. Agradecer nuevamente a CICESE por la confianza. Esperemos que en Veracruz sea igual de exitoso el evento que esta vez. Y aquí estamos para colaborar en lo que ustedes necesiten, propongan, para trabajar juntos siempre buscando el beneficio de la sociedad y tratando de impactar de manera positiva en el mundo. Así que nuevamente gracias por acompañarnos.
Bueno, pues creo que ya es hora de ir a comer. A menos que alguien quiera decir algo más del público, de los autores. Si no, pues vámonos todos de una vez a comer. Y doy por cancelado. Concluido virtualmente este congreso porque tenemos la cena y mañana los tutoriales.